Good afternoon. My name is Colton Wendler, and this is the Ultrasonic Transponder Senior Design Project. Today, I will be briefly discussing what an ultrasonic transponder is, followed by our progress on the project this semester, beginning with the requirements and documentation, followed by the receiver and transmitter circuits, followed by the Arduino signal processor, and finally, KiCad. The Ultrasonic Transponder project team is developing a system that uses two devices, at least one interrogator and one or more transponders. Both devices have a receiver and a transmitter. The interrogator transmits an on-off keying digital signal at a center frequency of 39 kilohertz to the transponder. The transponder receives it and transmits another unique signal back to the interrogator. The total time it takes to complete this cycle is then used by the interrogator to calculate the distance between the two devices. The Arduino has interfaced with the outside world on the interrogator device, while the transponder is self-contained. The receiver circuit is broken down into 5 stages: a transducer, followed by a low noise amplifier utilizing a JFET. Next is the amplification and bandpass filtration stages that goes into an AM detection board, and finally an Arduino signal processor. The transmitter circuit consists of 3 stages, beginning with the Arduino that feeds into an H-bridge, and finally another transducer. Due to the fact that our team could not go on campus early on, priority number 1 for the team was to organize documentation and refocus our overall efforts by overhauling the requirements document. The original document was fairly disorganized and hardly referenced. Our team created the new requirements document as a spreadsheet with multiple levels and a formal front page to keep track of changes made. Level 1 consisted of the project's driving requirements with 3 more levels, each of which containing requirements more specific than the level above.
You may need to unmute yourself.
Oh, sorry about that. The receiver subgroup inherited the receiver from the previous semester, which was functional but still had problems that needed to be fixed. One of the problems was that the high gain of the circuit was also amplifying the noise, which did not allow us to distinguish signals from a distance further than 6 feet. Bypass capacitors were added to the power supply rails to improve circuit stability, which are not shown in the above schematic. The transducer was also replaced with a more sensitive UTR 1240K TTR. A low noise amplifier utilizing a JFET that has a noise factor half of that of the op amp was then inserted between the transducer and the first op amp in an effort to reduce the effects of noise. The voltage divider between the second and third stage was replaced by a 1K ohm resistor, which then required us to transform the second and fifth stages from amplification stages to buffer stages to reduce the overall gain. Multiple bandwidth tests were performed, and currently the bandwidth of the circuit is 38 to 40 kilohertz. Another test that was performed several times throughout the semester was the range test. Next slide. The purpose of the range test was to determine the maximum distance at which the receiver can accurately receive a signal from the transmitter. The goal was to reach a distance of 45.83 feet. In order to conduct the range test, the transducer was connected to a signal generator transmitting a 5 and 10 volt peak-to-peak sinusoidal wave with bursts of 35 cycles per 100 milliseconds at a frequency of 39 kilohertz, with the receiver circuit upright and stationary. As you can see, there is 100 to 200 millivolts of noise. Beginning at 2 feet, the signal was sent and the voltage on the oscilloscope was recorded. The chart on the right shows the most recent range test. The 10 volt peak-to-peak signal was able to transmit clearly twice as far as the 5 volt peak-to-peak. This is prior to adding the low noise amplifier and reducing the gain. Next slide.
Hello, everyone. My name is Shine Rafar, and I will be presenting the AM detection circuit as well as the progress made by the transmitter subteam. The purpose of the AM detection circuit is to convert the on-off keying into a digital high and low signal that is fed from the receiver. This is a key component to this design because it is directly feeding into the Arduino itself. Before the physical circuit was built, the team used PSpice to design and simulate it. In order to recreate the signal input, we used 2 pulse generators and multiplied them together to act as a modulated waveform. As for the design itself, the team uses a precision half-wave rectifier or a superdiode as the first stage. As the input waveform is greater than 0 volts, the op amp reverse biases D3 and no signal will be passed through. However, if the input waveform is less than 0 volts, D3 will be forward biased and D4 will be reverse biased. This will configure the op amp to become an inverting amplifier, changing any negative signal to an equivalent positive signal. As for the second stage, a low pass filter is used to filter out any residual carrier and pass DC components to the rectified signal. Together, the two stages act as an envelope detector. This produces a signal that will be used in the following stage. The third stage is where the analog to digital conversion occurs. The op amp is designed in a way to force the analog signal to either high or low, based on its position when compared to the average amplitude of the signal. If the signal is above average, it will force a signal in one direction, and if the signal is below average, it will force it in the other. This way, there are only two possible outcomes from this stage, and a digital signal will be the result. Lastly, a 0 and 5 volt logic levels is being controlled by the transistor in the final stage. This circuit was built and tested in fall of 2020. Next slide. As you can see, the picture of the oscilloscope proves that the circuit changes the AM signal to a digital signal. However, there's one key feature to note. When the full amplitude carrier is present, the output is 0 volts. But when the carrier is absent, the output is 5 volts. This ensures that the absence of any signal represents a stop condition to the serial receiver in the Arduino. This way, at least one carrier pulse must be sent to alert the serial receiver that data is starting. Next slide. As the semester began, the team continued working on and finished the Halfbridge schematic that was decided on the previous semester. The team was having issues simulating the circuit in PSpice, so we decided that the design was simple enough that we could quickly construct and test it in the lab. Using a 5-volt signal generator to drive the transmitter, the team concluded that the resulting waveform from this design does not meet requirements. After a few weeks of research and deliberation, as well as discussing a problem with Professor Flynn, the team decided to complete the full H-bridge in order to pull up and pull down our signal to our desired waveform. Next slide. The team then continued by creating the full H-bridge design and running another test to see the resulting waveform. As intended, the H-bridge filled out the desired 10-volt peak-to-peak signal to our required specifications. Although the new signal very closely represents the desired output, there are a few experimental errors that may become issues when integrating all individual components together. The first and most concerning issue is a 2-volt peak-to-peak waveform that is produced by the transducer ringing post-pulse. The shape of the ringing is the result of the diodes in the bottom two transistors, Q5 and Q6, quenching the transducer after each pulse is ended as a way to ready it for each subsequent pulse. The NPN transistors prevent the ringing from getting above ground level, while the diodes prevent the ringing from falling below ground level. Second is the transient response that pulls the signal past plus and minus 5 volts. This is caused by the resonant frequency of the transducer itself. Lastly, as the semester ended, the team decided that it would be in the project's best interest to test the transmitter when integrated with the entire system to realize whether or not these discrepancies will pose risks in terms of signal processing. If so, further research, testing, and analysis will be done in the coming semester for the purpose of both improving the transducer quenching and reducing transient response. Next slide.
Hello, I'm Gabriel Gomez, and I'll be discussing our Arduino signal generation and processing. Our data signal generation and processing is performed by an Arduino board using the 5-volt serial interface. Data transmission is performed in 4-character keys, broadcast in the 10-bit serial, start bit low, end bit high serial format standard to Arduino UART. At the start of this semester, we used Arduino Uno boards, a low-cost model with a single serial port, but have proceeded to transition to using Arduino Mega 2560 boards at a moderately higher price point due to their 4 serial ports allowing greater interfacing options. Next slide. The interrogator and transponder are programmed with sketches, code created in the Arduino IDE based somewhat on C. An example sketch can be seen on the right side of the slide, which is a snippet taken from our interrogator code. The serial lines for both sketches are set to 400 baud rate. The interrogator device broadcasts a request key every few seconds, then listens in between pulses for responses. It calculates the distance between itself and any responding transponder using the round-trip flight time of the pulse based on the time sent versus the time a response is received with millisecond timing precision. This allows for a distance measurement with a precision accurate within 7 inches, is at our testing range. The transponder device waits and listens, broadcasting a response key whenever it receives a recognized interrogator key. Serial outputs link to the transmitter circuit, while inputs are fed through the envelope detector of the receiver circuit. Character inputs are stored in a character shift data buffer and tested for matches after every read character. A change was made to fix simulated input read errors, causing cascading inconsistency during processing in our previous implementation, which used a 4-stage for loop to pull data from the serial. Next slide. For user interface, a second 1200 baud serial line will be set up for the interrogator to print the ID and distance of any responding transponder. Testing of the sketches has thus far been performed with the Arduino IDE at 300 baud due to USB to serial limitations on baud rate. Plans for the future include linking an interrogator board to our transmitter circuit to determine if it will broadcast correctly. We also plan to test if the board can be fed from the same power supply as our hardware circuits, or if it will need a separate supply, or battery. Lastly, we intend to test if the data transmissions function properly at 400 baud linked to our completed hardware. I'll now pass it off to Ali Al-Shati to talk about our PCB development and KeyCat.
Greetings. The team have been using KeyCat to construct the PCBs of the circuits that were assembled in the lab. With DG's guidance, the team was successfully able to proceed forward with our AM detection PCB progress. As you can see on the screen, we have constructed the schematic on a schema for our AM detection circuit and have assigned each part to a footprint accordingly. For the LF411CP op-amp that you see, we have exported its symbol and footprint from Snap PDA, since KeyCat's library does not include that specific op-amp. Next slide. Moving on, the team have created a netlist for the AM detection schematic and exported it to the PCB layout editor. We organized and traced each part to the assigned parts accordingly. The ground nodes were connected using a copper port in order to make the milling process easier and also to reduce radio emissions. We ran the design rules check, and thankfully the test came out with no issues, so we were able to proceed without any problems. The Gerbers were plotted for the copper, silk, mask, paste, and edge cuts layers, and were compiled and sent to Ashbrook for production. Now we wait for the PCBs to arrive in order to do further testing with them in the lab. And by that, we conclude our ultrasonic transponder presentation. Any questions?
Okay, thank you. Are there any questions from the audience or the judges?
Yeah, this is Vaughn Cable. I have a question. You mentioned you were multiplying two sinusoids together as part of the modulation scheme. Is that right?
Yes.
And then how did you get the how did you get the pulses?
I'm sorry, can you
How did you get the two modulations, two sinusoids gives you multiplied, gives you the sum and difference in sinusoids. How did you chop that into square waves?
so to be honest, I'm not quite sure how to answer your question. This is a method that we've been using to test all of our components. We use two different sinusoidal bursts to and multiply them using different methods. But in this schematic, we use multiplication to combine them to get a fully modulated wave that simulates what the receiver will be getting and feeding
Okay,
to the
I
AM
understand.
detection.
I understand. Your sine waves are already chopped. They're already in a on-off mode,
Yes.
and you just synchronize the two. Okay, what's a super diode?
So a super diode is so that's the first op amp stage there, the LF 741. What it does is it acts as an ideal diode in ideal situations without voltage drops. Since the voltage that we're using is very low, the voltage drop would be significant. The way that it works is it generally just it acts like a rectifier, as if you know, you would use the diode or configuration, except it negates the voltage drop that would be a characteristic of that
I-
build.
Of a diode, right, of a typical silicon diode or something. Okay,
Yes.
great. Uh, did anyone do any stability analysis? You mentioned ringing, and you mentioned overshoot and other things. Anybody do any stability analysis of each of the op amp stages?
For the
In-
AM detection board or the receiver or the transmitter?
I can actually answer that question.
Okay.
So we took over in fall. The previous semester, yes, they have done stability measures. And so from then on, if we make major changes, we will continue to do those, but we haven't had to reassess that yet. We're still working on some other parts of each circuit.
Did you do the stability analysis in PSpice?
I'm not entirely sure what method the previous semester used, but the stability analysis was done.
Okay, because that may not have been thorough because of the ringing and some other issues that you're having to deal with. And what's the did you mention something about 7 inches, plus or minus 7 inches, or to within the ranging to within 7 inches? Does that meet your requirement?
Yes, our initial requirement was accuracy within 1 foot. It was determined that millisecond precision at the speed of sound, and sound travels just over 1 foot per millisecond, and at our current altitude, and that does not change significantly for the vast majority of altitude ranges where people live. So yes, the accuracy was determined to be accurate within 1/2 of that due to millisecond precision. So it was considered to be acceptable.
Okay, all right, thank you. Yeah, one last thing is you basically you have the transponder responding with a did the transponder repeat the signal?
The transponder has its own unique key. The interrogator that is separate from the interrogator key. So both the interrogator and the transponder have a key library for their associated system.
I understand. Now, but what I'm saying is the transponder, did that, what was the information that was retransmitted by the transponder?
The transponder sends only its 4-character identification key. Ranging is done entirely on the interrogator side using round-trip flight time and for measurement. Currently,
So unfortunately, I'm gonna have to end it there. Where I don't want to run behind. But thank you for the
Okay.
questions.
Yeah,
So
I
thank you.
understand though.
Yeah, I apologize for interrupting. Thank you to the Ultrasonic Transponder team and the judges for their great questions. And so this was the last project for the Electrical and Computer Engineering Department. Again, I'd like to thank the judges, Mr. Bott and Mr. Cable, for their great input.